Okay, hello again, and thank you for hanging in there with me this Monday morning as we discuss this example, or we look at this example of possibly composing two functions, f and g, and what we can do to use the information from one function to evaluate the other function. So again, we have function g that takes an input that is a side length of a square in meters and gives us an output area of the square in square meters. Okay, in a moment I will define a variable s that will take on all the values of the length of the side of the square in meters, and I will also define a variable capital A that will take on the values of the area of a square in square meters. Then we have this function f on the right. Looks like it's linear. You might want to check what the constant rate of change is. The input quantity is, again, side length of a square, so that's the same quantity that we have as an input quantity in the first function. However, the output of function f is the perimeter of a square, which is just in meters, not square meters. And so we'll define a variable p to take on those positive values. Okay. If you think through the correspondence of these quantities, where we've defined the three quantities s, length of the side, p, length of the perimeter of a square. Both s and p have the same units, meters, but they are different quantities. A has a different unit, meters squared, and it's a third quantity, area of the square. The linear function on the right graph that I've covered up would be function f applied to input s. The output would be quantity p. So f assigns to each value of s a positive perimeter p, which is the sum of the four lengths of the sides. I think f was the green function, so we'll go to green. And another way to write s plus s plus s plus s would be 4s, collecting like terms. On the other hand, if you look at function g, I'm going to roll this paper back. Function g is nonlinear, does not have a constant rate of change. But we know how to find the area of a square. So if we apply rule g to input quantity s, we will get an output quantity a, area of the square, if we take the length of one side times itself. And we know another way to write that is s squared. So they didn't write it in your Pathways student textbook. The author didn't. But function g, on the left graph is a quadratic rule, s squared. And the value of s that they've displayed would be positive values, and maybe 0, though we wouldn't have a square. The rightmost graph was the linear graph, f of s plus 0. If you look back, the graph goes through the origin. Okay, well, I'm getting a little off topic of composition and inverses, but I did want to come up with an algebraic way of describing the two functions, one of whose output is area and the other whose output is perimeter. Okay. After watching that Patrick JMT video that was assigned first on basic inverses, you will hear Patrick talk about input-output and inverse functions that take the output of one function and trace back to the input of the original. So I want to describe here, using the graphs in a minute, an inverse rule of g. But when we talk about the inverse rule of G, the input quantity would have to be the area of the square, and the rule would need to get us back to the side length. Then we could compose F and G inverse. Just of note, area would end up being a non-negative quantity. To reverse or undo this linear rule, F that assigns to each S a perimeter, if we want an inverse rule, F inverse, we would apply our inverse rule to the perimeter of a square and get back to the length of the side. I'm being pretty abstract now, but I'll get more concrete with the graph. Because what I wanted to go with here is to show that G must be composed with a function whose output would be S. So if our first video where you were working with me had been a composition of G and F inverse of P, you would get the result would be the area of a square with perimeter P. Pardon the awful writing there. And let's see if I can go on just a little bit more with that idea. And again, you need to watch the at least my video that I titled Video 2 out there. Composition of two functions only works if the input of one is the correct input. Up here, green, F is only defined for quantities S. So G inverse of A would give us an appropriate quantity to put back into F. And the result would end up being the perimeter of a square with a given area. Okay. Now we're at about the 8-minute mark, about 10 seconds after, because this is where you might want to go and rewatch some of the graphing here. Let me pull this aside and we'll look first at this second composition. The output of my composition is a perimeter. Given an area A, let's say we're given an area 4. No, I said that wrong. Well, let's say we're given an area that's 4. Here's the 4. Given an area with value 4, that would correspond to a side length of 2. And then the side length of 2 would correspond to this point on function F. That would give us a perimeter of 8. So F applied, excuse all the hopping pens, to G of 2, G inverse of 4, excuse me. F applied to G inverse of 4 is equivalent to F applied to 2, and F of 2 equals 8. Okay. Quickly through one more example, because I know you can go back and do some of this on your own. Let's take a perimeter of 12. If we pull that back to function F, a perimeter of 12 corresponds to a side length 3. And if we have a side of length 3, the area of our the area of our square would be 9. So G applied to F inverse of 12 is going to be the same thing as G applied to 3. And G of 3 gives us an area which is, I'm off the page, an area which is 9 meters squared. Thank you for working with me in this, with the technology, and good luck with your continued studies on 1, composition of functions, which is in this section 3.4, and then your continued studies with inverses, which is the pathways section 3.5.